Audio recording lectures for visually impaired students. Modern approach to organic chemistry, BSc Part 1 by Dr. J.M. Sehgal. Chapter 3 Dienes Introduction. The alkadienes, or as they are more commonly known, the dienes, are unsaturated hydrocarbons containing two carbon-carbon double bonds per molecule. They have the general formula CnH2n-2 and are isomeric with alkynes, but the behavior of dienes and alkynes is quite different from each other. Classification. Dienes are divided into three classes depending upon the arrangement of double bonds in the molecules. They are classified into three classes. First one is isolated dienes. The dienes in which double bonds are separated by more than one single bond are called isolated dienes. For example, 1,4-pentadiene, 1,5-hexadiene. Second, cumulated dienes. The dienes in which the double bonds are present between successive carbon atoms are called cumulated dienes or allenes or cumulanes. For example, 1,2-propadiene or allene, 1,2-butadiene or methylalene. Number 3. Conjugated dienes. The dienes in which the double bonds are separated by a single bond are termed conjugated dienes. For example, 1,3-butadiene, 2,4-hexadiene. Nomenclature. Cumulated dienes are commonly named as alkyl derivative of allene CH2 double bond C double bond CH2, which are simplest member of this type of dienes. For example, methylalene, 1-ethyl, 3-methylalene, 1,1-dimethylalene. A UPSC nomenclature of all type of dienes is similar to that of alkenes, except that the numeral di is added before the suffix "-ene" to indicate the presence of two double bonds. For example, 1,2-propadiene, 1,2-butadiene, 1,3-butadiene, 5-methyl, 1,3-hexadiene, 1,5-heptadiene, 2,7-dimethyl, 2,5-octadiene. Relative stabilities of dienes. It is interesting to note that the difference in the relative location of the double bonds in their molecule causes appreciable difference in the relative stabilities of different classes of dienes. The data on the heat of hydrogenation. It is interesting to note that the difference in the relative location of double bonds in their molecules causes appreciable difference in the relative stabilities of different classes of dienes. The data on heat of hydrogenation of alkanes and dienes clearly show that the conjugated dienes are more stable than the non-conjugated ones. For a diene, the total heat of hydrogenation may be expected to be the sum of heat of hydrogenation of individual double bonds. This is found to be so for non-conjugated dienes. For instance, the observed heat of hydrogenation of 1,4-pentadiene is 254.4 kJ per mole, while the expected value is 251 kJ per mole. But in case of conjugated dienes, like observed value are lesser than the anticipated values. For example, the actual heat of hydrogenation of 1,3-butadiene is 238.2 kJ per mole, which is 12.8 kJ lesser than the expected value. Similarly, the heat of hydrogenation of 1,3-pentadiene is about 16.7 kJ lesser than the expected value. Now to isomeric dienes, which differ only in the relative location of double bonds. Example, 1,4-pentadiene and 1,3-pentadiene give rise to the sum alkane on hydrogenation. Still, if the conjugated diene evolve lesser energy than the non-conjugated one, only means that the former contains lesser energy than the latter. In other words, conjugated diene system is more stable than non-conjugated diene system. The greater stability of conjugated dienes may be explained in terms of resonance and delocalization. Structure of 1,3-butadiene. It has been stated above that conjugated dienes are more stable than non-conjugated dienes. The extra stability of conjugated dienes can be explained in terms of their structure as discussed below by considering the structure of 1,3-butadiene. Resonance structure. Unlike non-conjugated dienes, conjugated dienes exist as resonance hybrid of various contributing structures. For instance, 1,3-butadiene is a resonance hybrid receiving contribution from many structures, the more important of which are. It should be noted that the structure second and third involve separation of charged particle. As such, structure one which does not involve any separation of charges is the most stable and therefore the most important of all contributing structures. The actual structure of 1,3-butadiene is a resonance hybrid which lies somewhere in between the contributing structure but resembles the structure 1 more closely. This means that the bond between C1 and C2 and C3 and C4 is not a pure double bond but quite close to it. Similarly, the bond between C2 and C3 is in between a single and double bond but nearer to single bond. This is in keeping with the fact that the bond length between C1 and C2 or C3 and C4 is nearly the same as that of C double bond C, while the bond length between C2 and C3 is somewhat lesser than of a C single bond C single bond. Thus, the relative stability is greater. Methods of formation of dienes. Dienes are generally produced by suitable variations of the methods employed for the preparation of simple alkenes. The more commonly employed methods are given below. First, catalytic dehydrogenation of alkenes and alkenes. For example, 1,3-dienes may be prepared by passing the vapors of N-butane over heated Cr2O3/Al2O3 catalyst. 1,3-butadiene is also obtained by passing the vapors of 1-butene or 2-butene over heated nickel phosphate or calcium phosphate. Number 2. Dehydrohalogenation of dihalogen derivatives. For example, on heating with alcoholic potassium hydroxide, 1,3-dichloro-3-methylbutane give isopropene. 3. Dehydration of diol in presence of acid. For example, dehydration of 1,4-butadiene by heating in the presence of sulfuric acid or phosphoric acid result in the formation of 1,3-butadiene. 4. Pyrolysis of cycloalkanes. For example, 1,3-butadiene can be prepared by the vapors of cyclohexene over heated nichrome. Chemical reactions of dienes. The chemical properties of diene are essential due to the presence of two carbon-carbon double bonds in their molecules. Thus, non-conjugated dienes behave in exactly the same manner as simple alkenes, except that the attacking reagent is consumed in twice the amount required for one double bond. In case of conjugated dienes, however, the properties of the double bonds are considerably modified due to the characteristic relative arrangement of double bonds. This relative arrangement enables the two double bonds to interact with each other so to modify the behavior of molecules as a whole. The conjugated dienes are characterized by their greater stability and occurrence of 1,4 addition reactions. The important reactions of dienes are discussed below to illustrate their behavior. Electrophilic addition reaction 1, 2 and 1,4 addition reactions. Dienes undergo the usual electrophilic addition reaction shown by alkenes. However, due to the presence of two double bonds in their molecules of dienes, The total quantity of addendum is naturally 2 times that required for an alkene. The important electrophilic addition reactions are given below. First, addition of halogens. When treated with halogens, dienes reacted with 2 more of moles of halogens per mole of dienes to form tetrahalogen derivatives. For example, the really interesting point, however, it is what happens when the 1 mole of the addendum is made to react with 1 mole of diene. In such a case, the 2 double bonds in a conjugated diene act independently of each other and addition takes place across either of the double bonds. For example, 1,4-pentadiene is converted into 4,5-dibromo-1-pentene. But a different situation prevails in case of conjugated dienes. To illustrate it, let us consider the addition of 1 mole of bromine to 1,3-diene. The product obtained consists of a mixture of 3,4-dibromo-1-butene and 1,4-dibromo-2-butene as shown below. The formation of 3,4-dibromo-1-butene is not surprising as it is the result of normal addition to adjacent carbon atoms linked by a double bond. But the formation of 1,4-dibromo-2-butene due to 1,4 addition appears to be unexpected. Mechanism of 1,2 and 1,4 addition to conjugated dienes. Mechanism of 1,2 and 1,4 addition to conjugated dienes. To understand the occurrence of 1,2 and 1,4 addition reactions, let us examine the mechanism of addition of bromine to 1,3-butadiene. The reaction takes place in 2 steps through the initial formation of allylic carbocation. First, the formation of carbocation. As the bromine molecule approaches the diene and gets polarized, the positively polarized bromine adds to C1 of butadiene to form an allylic carbocation A and a negative bromide ion. A primary carbocation CH2 double bond CH single bond CH Br single bond CH2 positive could also be formed by the initial addition of bromine to C2. By the ion A is formed in presence to this primary carbocation as the former is not only a secondary but also an allylic cation which is stabilized by resonance between structures A and B. The two contributing structures A and B differ from each other in the location of double bonds and of positive charge. In resonance hybrid of these structures, the positive charge is not localized on C2 and C3 but is spread over both as shown below. Number 2. Addition of bromine ion. It is clearly that there are two positive charges centers in the cation which may be attacked by negative bromide ion in the second step of addition. Addition of bromide ion Sc2 would give 1,2 addition product while addition of bromine ion at C4 would give 1,4 addition product. Number 3. Addition of halogen acid. Addition of halogen acid to conjugated diene are similar to addition of halogen. Addition of 1 mole of halogen acid to a conjugated diene give rise to both 1,2 and 1,4 addition products. For example, 1,3-butadiene gives 3-chloro-1-butene or side product as 1-chloro-2-butene mechanism. To start the reaction, a butadiene molecule abstracts a hydrogen ion from hydrogen chloride and form an allylic carbocation C and a negative chloride ion. Initial addition of hydrogen ion could also take place at C2 given a primary carbocation CH2 double bond CH single bond CH2 single bond CH2 positive, but the ion C is formed in the presence of this primary carbocation as the former is not only a secondary but also an allylic cation which is stabilized by resonance between structure C and D. The resonance hybrid of these contributing structures may be represented as shown below. Thus, there are two positive centers which may be attacked by negative chloride ion in the second step of addition. Addition of chloride ion at C2 would give 3-chloro-1-butene while addition at C4 would give 1-chloro-2-butene. Effect of temperature on 1,2 and 1,4 addition of conjugated dienes. It has been found that the ratio of in which the 1,2 and 1,4 addition product are formed in a result of electrophilic addition to conjugated diene is largely governed by temperature at which the reaction is carried out. Generally speaking, 1,2 addition product is formed preferentially at lower temperature while 1,4 addition product predominates at higher temperature. For example, explanation of the effect of temperature on 1,2 and 1,4 addition. The effect of temperature on 1,2 and 1,4 addition reaction may be attributed to the following reasons. First, E activation leading to 1,2 addition product is lesser than the leading to 1,4 addition product. As such, the 1,2 and 1,4 reactions may be more readily than 1,4 addition. However, the 1,4 adduct once formed is more stable than 1,2 adduct. Number 2. Both the addition product can undergo ionization forming a common carbocation. This leads to an equilibrium between the two product and carbocation as shown below. Since the energy difference between 1,2 adduct and carbocation 1 is lesser than between 1,4 adduct and the carbocation, ionization of 1,2 adduct take place readily while that of 1,4 adduct take place slowly. At room temperature, ionization of product occurs to a very small extent only so that 1,2 adduct which is formed faster is main product isolated. This means that at lower temperature, the relative amount of the two products obtained are in accordance with their relative rates of formation. In other words, the reaction is kinetically controlled. At high temperature, ionization becomes more important. The 1,2 adduct, which is thermodynamically less stable, readily ionizes, while the 1,4 adduct, although formed slowly, does not ionize readily. As such, 1,4 adduct is present in large quantity when the large equilibrium is reached and therefore is the main product obtained. In other words, at high temperature, the reaction is thermodynamically controlled. Number 2. Free radical addition reaction. Like simple alkenes, conjugated dienes also undergo certain free radical addition reaction in the presence of suitable organic peroxide. Moreover, addition of free radicals can again lead to the formation of both 1,2 and 1,4 addition product. For example, mechanism. The mechanism of free radical addition such that given above may be summarized as follows. It may be noted that the allyl free radical formed in step 3 is resonance hybrid of the structures E and F. In the resonance hybrid, the odd electron is distributed between C2 and C4. As a result, this allyl free radical can form either 1,2 or 1,4 addition product by abstracting a bromine atom from another molecule of PrCCl3. The newly formed CCl3 radical then carries on the chain process. It is very interesting to note that the free radical addition to conjugated dienes proceed at much faster rate than the similar reaction with simple alkenes. Even it is interesting to note that the free radical addition to conjugated dienes proceed at a much faster rate than similar reactions with similar simple alkenes, even though conjugated dienes are themselves more stable than simple alkenes. This unexpected reactivity of conjugated dienes towards free radical addition is attributed to, the much greater stability of the intermediate allyl free radical as compared with the intermediate free radical formed from simple alkenes. Therefore, the E net for the formation of intermediate allyl free radical is lesser than E activation for the formation of intermediate free radical in case of simple alkenes. As such, the free radical addition to dienes take place more readily and at a faster rate. Number 3. Diel-Alder reaction 4 plus 2 cycloaddition. This is one of the most important reactions of conjugated diene. It involves an addition reaction between a conjugated dienes and a compound containing a double bond called a dienophile to form a six-member ring. Since the reaction involves the addition of a 4 pi electron system to a 2 pi. Since the reaction involved the addition of 4 pi electron system to a 2 pi electron system and lead to the formation of a cyclic product, it is often referred to as 4 plus 2 cycloaddition reaction. The product form is often called a di-Elder adduct. The simplest example of di-Elder reaction is that between 1,3-butadiene and ethylene, that is dienophile, but the reaction takes place very slowly and in low yield. The reaction takes place by a concerted single-step mechanism during which C1 and C4 of the conjugated diene system get attached to the double-bonded carbon of the dienophile. As a result, the two new sigma bonds are formed at the cost of 2 pi bond of the diene and the dienophile, as is clear from the above example. Di-Elder reaction take place very rarely when substituted alkenes containing electron withdrawing group are used as dienophile. For example, first reaction between 1,3-butadiene and acrolein, that is dienophile, take place 373 Kelvin to form adduct in quantitative yield. Number 2, malic anhydride, that is also a dienophile, react readily with 1,3-butadiene at room temperature to give quantitative yield of the adduct, factor which favored the reaction. It was originally stated by Elder that the reaction is favored by the following factors. First, the presence of electron withdrawing group in the dienophile. The favorable effect of electron withdrawing group in the dienophile is very clear from the example given above. It has been seen that the acrolein and malic anhydride undergo di-Elder reaction in quantitative yield even under mild condition. Number 2, presence of electron releasing group in diene. 2,3-dimethylene 1,3-butadiene offered an important example of diene to demonstrate the favorable effect of electron releasing group in the diene. The conjugated compound containing 2-methyl is about 5 times more reactive in di-Elder reaction than 1,3-butadiene. For example, 2,3-dimethyl 1,3-butadiene react with acrolein in quantitative yield at only 303 Kelvin. As against this, 1,3-butadiene react with acrolein in quantitative yield only at 373 Kelvin. Stereochemistry of Diels-Elder reaction. The di-Elder reaction is highly stereospecific. The important aspects of this stereochemistry are as follows. First, S-cis conformation of dienes. The diene undergoing the reaction must be in S-cis conformation rather than S-trans conformation. This is because only the S-cis conformation allows the end of conjugated system to reach the double bonded carbon of the dienophile. Number 2, occurrence of syn addition. The reaction takes place by syn addition of the diene to the dienophile and the configuration of the dienophile is retained in adduct as illustrated below. Synthetic utility of Diels-Elder reaction. The synthetic utility of the reaction lies in the fact that it can be used in the preparation of many cyclic compounds which would be difficult to prepare by other means. A prominent feature of all reaction is that it is extremely easy to carry out. In most cases, the reaction is brought about to merely heating the reactant together with or without a solvent. Number 4, polymerization reaction. Conjugated diene have a strong tendency to go under free radical polymerization to form useful high molecular weight polymers. Number 1, polymerization of 1,3-butadiene. Peroxide induced polymerization of 1,3-butadiene give rise to polybutadiene. The formation of polybutadiene involves predominantly 1,4 free radical addition of diene unit to each other so that the product obtained still contains a double bond for each butadiene unit. Number 2. Polymerization of 2-methyl 1,3-butadiene. The free radical polymerization of 2-methyl 1,3-butadiene or isopropene gives polyisopropene which resemble natural rubber.